introduction of DL4CV. So today we'll talk about the object detection methods and we'll look at its implementation. And post that we'll also discuss the questions of the assignment 6 and then we can take the questions in that. Okay, so starting with object detection methods. So this talk is basically focusing on CNN-based object detectors, and they are generally two-stage detectors. So in the two-stage detectors, we can have the first stage. I couldn't get the classroom today, so I have to be here. I'll try just to excuse me. Actually, I'm taking one session online. So can you please keep all of the video? So will this be okay now? Okay, sure. So we're here. Let's restart. Okay, so today we will be starting with CNN-based object detectors method, and they are basically categorized into two types. The one is the two-stage detectors, and the second is a single-stage detector methods. Now, when we talk about two-stage detector methods, generally we have in the first stage we try to propose certain areas or the boxes in an image where we assume that the object will be present, and the second stage will be then to refine these bounding boxes. Now in this first stage, when we're proposing a set of bounding boxes or set of regions in an image which can have the objects we are looking for, this can be either done using a CNN-based approach or some non-CNN-based approach, like using main shift algorithm for segmentation or graph-based segmentation approach. In case of single stage detection methods, we rely completely on the network to select. So it's a single stage. What we mean by that is we just give an image to the network and it will directly give us the coordinates of the bounding boxes as well as the probability of the class present in those boxes. So starting with now two-stage detector methods, and the first one we will be looking is RCNN. Right. So the slides for RCNN. Yes. 1 minute. So so when we talk about this RCNN, what happens is that the problem was okay. So when we talk about this RCNN methods, right? So we had this region proportion using selective search algorithm, and we were getting around 2,000 regions, right? And then we were passing each region to the CNN network to predict the bounding box coordinates and the probability of the class present in that bounding box, right? So the issue here was that it was taking a lot of time because we were depending on some algorithm which can give us the set of these region boxes which can have these objects. As an improvement in this first RCNN method, where we tried to replace this region proposal. So initially what was happening is that suppose there is an image, okay, when we call cricket, let's say using selective search algorithm, we found 2,000 possible regions for the candidate region. And now when we passing each region from this network to get the refined bounding box coordinates and the probability of the class present in that region. And this was taking I think right now it's not noisy. There might be some issue with your channel. Is anyone else also finding it noisy? I'm not sure because Okay, let me rejoin the meeting then. Hello. Is this okay now, or is it still noisy? Hello, everyone. Is this okay now, or is it still noisy? No, so we were talking about this fast RCN method, right? So what I was saying is that when we use the selective search algorithm and get a candidate set of, let's say, 2000 bounding boxes. So the issue was that we had to pass each result independently from the network to get the coordinates of the bounding box and the class probability. And this was taking a lot of time, right? Because if there are k bounding boxes predicted, or you should predicted using selective search for one image, to find the possible set of bounding the objects, detecting objects in that image, it will be taking k times forward passes, right? So first RCNN, what it did is that it tried to do one single pass through an image, get a feature map, and then it directly tried to use these features, these regions which were selected using this region proportional network or any other method directly on that feature map itself. Okay, and then it made the predictions. So that way it tried to save a lot of time. And then came the first RCN, in which instead of relying again on this another segmentation based methods like selective search, they proposed their own network, which is known as the region proportional network, to propose a set of candidate regions and then refine those candidate regions further using these the second stage of the detector. Okay, so this was the two-stage detectors, but so today in this talk we are mainly going to look on the single-stage detectors, which is YOLO and SST. So sorry, I did not full screen. So looking at YOLO, what YOLO does is it means you only look once, and it actually gives you the coordinates of the bounding box as well as the class probability at once. So there is only a single pass. So suppose here is an image, and the goal is that we want to detect this dog and the bicycle in an image. And so what we want as an output is the coordinates of these bounding boxes and the class which the object, like the class of the object present in these boxes. So this is the desired output. And so what this YOLO does is that it will try to divide this image into a grid of S cross S size. So generally I think S is equal to 7 in YOLO 1. So if we look at this particular figure, you'll see that in this image we have divided this image into a grid. Okay? And each cell in this grid is corresponding to one region in an image. And now what YOLO will try to do is that it will say that, okay, for each cell of this grid, we will predict P bounding boxes. So it means that each cell is then predicting some set of coordinates, and those will be actually equal to P. So each cell is predicting P boxes. So it's like total number of bounding boxes predicted here will be S into P. And apart from that, what it will predict is that for each grid cell, it will predict the class probabilities. So like let's talk about this particular cell here, in which we can say most of the chunk of this dog is present. Okay, so this cell will be predicting B bounding boxes, which means it will be giving you the coordinates of B boxes and also the class probability that if there's any object present here, then which object will it be? So using this predictions, we get a class probability map. So suppose this blue represents the class term, then it says that for these specific cells, the probability of finding dog is high. For these specific grid cells, the probability of, if pink represents the background, maybe then it says that okay, the probability here of finding any class is very less. And similarly for the yellow, which may correspond to the bicycle, it will be showing that these are the cells where you can find a bicycle and so on. So you get a class probability map where each grid cell gives you the probability of the most likely class it can contain. At the same time, along with this class probability map, we have bounding boxes and their confidences. What it means is that per grid cell, we will have B bounding boxes into 4. So basically for each bounding box, we need 4 values to be predicted, which will be the center of the coordinates and the height and width of the coordinates. So that is, per bounding box, we have 4 predictions, which are predicting its size. And then one more prediction, which is predicting the confidence of the bounding box. That is whether there is an object or not. Okay, so there are total of 5 predictions per bounding box, and we are having B bounding boxes per grid cell. So total number of predictions will be basically S cross B into 5. And that is information we're getting for these bounding boxes, and there is this one class probability. And when you combine these two and these final detections, so that's the idea of the YOLO, that it just provides us. You do not need a separate network to predict the regions for you, and it will do these things. However, the issue here is that if you look at it clearly, you'll see that each cell is responsible for detecting exactly one bounding box, because we are predicting exactly one set of class probability. Now this issue was being refined in YOLO version 2, where we have anchor boxes introduced similar to faster RCNN. So now each cell can predict, can have K, like each cell can now be responsible for predicting more than one bounding boxes. And this is done basically, here you will have K bounding boxes per cell, and all these K bounding boxes will have their own probability score instead of having one probability score per cell. So this is the improvement results in a neural network known as YOLO version 2. The another very famous single stage detector is this SS3, in which we try to have multiple scale feature map detection. So what we do is that given an image, we pass it through a network. It can be VGG, it can be ResNet. Generally, the backbone is VGG, but you can try with other backbones as well. And what will happen is that as you will keep on applying the convolutional layers, the resolution or the size of the feature map will keep on reducing. So we will have some higher resolution feature maps in the initial stages, but they will be capturing more low resolution features. There will be low resolution feature maps in the deeper layers of the network, but they will capture more abstract information. So what this suggests is that we can use these feature maps of different scales to predict the objects which may be present in an image at different scales. And for this, what they do is they take the feature map output from multiple convolutional layers and they try a detection over these feature maps. And then we have this non-maximal suppression to remove the bounding boxes which are overlapping and predicting the same or very close by predictions. So basically, we have the bounding boxes corresponding to the same counter box, but slightly shifted. So we try to minimize it, and for that we use non-maximal suppression is done. And this is how we can use the single shot detector method. So here we are just doing, so basically the size of the feature map. So suppose here is the feature map you get, okay, and the size of the feature map is, let's say, H close to blue. Then for each cell here, that is total will be HW, we will be predicting K bounding boxes. So it will be HW into K. Okay, so this is single shot detector. However, the issue with the single shot detector methods is that we have a lot of high number of uh, possible bounding boxes to be predicted, right? If you see, even in this case of YOLO, the number of bounding boxes which we were predicting is S into S into B. However, there are only two round-trip bounding boxes. So this results in a very highly imbalanced ratio of positive to negative situation. And therefore, to avoid this, there is another network called as retinal net, where we have this focal loss, where we try to make sure that if once the probability for the correct class is high, the loss incurred should be reduced. Okay, so that was the another network retinal net, which is there in the slides. But I just wanted to mention about this highly imbalanced ratio between negatives and the positives. So this is how this particular thing is done. So suppose this is an image, there are these ground truth bounding boxes, and we have talking about this 8x8 feature mapping. Now for each cell in this 8x8 feature map, we will be predicting k anchor boxes, and these k anchor boxes are of different scales and shape. So one is elongated towards the y-axis, one is elongated towards the x-axis, one is a perfect square, one is a smaller square, and so on. And the aim will be to predict the probability score for each bounding box as well as refine its coordinate. So if we have this edge cross double feature map, here when we will look at detections per class, what will happen is that per cell here, we will have k bounding boxes. For each bounding box, it will predict the location of cell and the class score. So this also has this non-maximal suppression, right? So this non-maximal suppression says, suppose there are two bounding boxes, B1 and B2. And if most B1 and okay, so if the overlapping between B1 and B2 is very high, then we can just select one of them. So how we do is that for this we compute this IOU score, which is intersection over unit, and this is defined as the intersection of these two bounding boxes B1 and B2 divided by the union. So that is B1 union B2, and based on this value, we decide whether we should keep both the bounding boxes or we should keep only one boxes. The idea is that if there are two bounding boxes which are very close to each other, there is a small offset with respect to the location, then there is no point of having more than one. So for example, if you look here, these are the bounding boxes, right? They are very close, where they all are representing this phase. So there is no point in having these three boxes. Just keeping one of them is sufficient. So there, this non-maximal suppression comes, and all these three bounding boxes, out of these three, only one is captured because here the IOU will be greater than 0.5. Okay. Now, the next is this image segmentation topic, in which the aim is that we want to assign to classification per pixel. So what it means is that there is this image, right? If you look at the image, if you look at the pixels of this car, then they should be categorized for class car. If you look at this area colored in pink, then they should be categorized to class road. If you look at some other pixels here, then they should be categorized as background class. So image segmentation basically refers to classifying each and every pixel in an image to one of the classes, and the classes can be the set of objects we are interested in. So here we are interested in car, the roads, maybe the traffic lights or traffic signs. So each and every pixel is being now categorized into those classes, and the other class is the background class, which is this, where the pixels are not being categorized further. The other application of this image segmentation is that suppose you have this MRI scan, the CT scan of your brain, and you want to detect some kind of tumor, right? So then you can then start categorizing each image here, tumor, to some specific subsection of the brain. You can start categorizing each pixel here And based on categorizing each pixel to those specific classes, you can find a match which will be categorized to the same class, right? And that will help you in segmenting the ground truth pixels and segmenting out the this image into interesting regions. Okay, and this interesting region will be depending on your problem at hand. The next I wanted to talk about is this encoder-decoder architecture, and this is mainly used for upsampling. So basically what happens is when you give an image as an input to the network, you can get some digit representation here, right? And but the issue is that that will be very low resolution to us, right? And we want something as good as the original image shape. In that case, we need to upsample these layers, right? And there's this decoder pack. So idea is that given an image, you get a latent representation, you upsample it, and this, whatever you get at the output, this should be very similar to what you get at the input, and that is the encoder-decoder architecture. But here what I want to emphasize is on these upsampling layers. So these upsampling layers are important when you want to map these low resolution feature maps to high resolution feature maps for better understanding of segmentation or classification or any other task. And we will look at its implementation, application, especially in case of unit. So this is again encoder-decoder architecture, but with skip connections. So here what we are saying is that once we get this image as an input to the network, we get this feature map, we get the next one. But here, this input is also directly correlated with the input we get here. So what is being meant here? This is somewhat similar to unit, right? You keep on downsampling here, and at the same time keep on upsampling, but we want to maintain the information between the same stages of upsampling and downsampling to be similar. So suppose when we are downsampling it after this one stage, and the information which we are getting just before the last upsampling should be very similar. The information loss should not be much. And we will just look at its implementation. This is just a small item. Now we will just go to the implementation of unit. So there are two implementations today I want to talk about. One is about the contrastive learning, and the one is regarding the segmentation using unit. So starting with series for segmentation code, let's look at it. So you all are clear with what segmentation is, right? So in this notebook, we are trying to implement unit to segment images, and as a just for understanding purpose, in this notebook we will be creating a dummy dataset. Our dataset will be comprising of black images but with certain objects, and these objects will be either a triangle or a square or some kind of mesh. Let me give you an idea of this. So this is this kind of dataset we will be generating here. A black image, but with some objects present in these images at random locations, and these objects will be of this size shape as like this hexagon or a circle, a filled circle, just a loop here, a triangle, a square, a small mesh, and a filled square. And this data set on which we will be training unit will basically comprising of so many images, but with random location of these set of objects. Okay, and the aim will be to segment these objects in these images. Okay, and this is our aim. And so when we are generating this data set, and when we aim to train unit on this data set, we also need the ground truth mask, which this unit will be generated for us. So in that case, this will be the ground truth mask. What it means that when we will try to segment this image, this is how the output should be, that this plus should get one class, this sphere circle should be an instance for another class, this mesh should be here as blue, and so on. So these different colors are representing each class we are interested in, and the aim is that each pixel here should be categorized to one of these classes. Okay, is this clear? Okay, so moving ahead, and now given this ground truth images and the target mask we are interested in, we want to train a unit. Okay, so starting first with how to generate this data. So for generating this data, what we will be doing is we have written certain helper functions. So first is to generate this random data, in which we will be calling this function image and mask. So this will be generating those black images with objects and the corresponding target mask. So here, whatever the size of the image we want, that we will pass as an argument. And now within this space, randomly a location is chosen for a triangle, a circle, two circles, one mesh. So though they are two circles, but they are different, right? One is filled circle and one is just a loop. A mesh, a square, and a plus. So randomly a location is being selected in this image using this get random location function. So get random location has been defined here, which takes this width and height as an argument, and it randomly selects an image. The zoom function ensures that when we are selecting the size, we can control the size of that object. Otherwise, it might become difficult. Okay. And then once we have selected these objects at their locations, now the next step will be to add these objects. So for that, we will call these corresponding function. For example, adding the square. So ARR represents the image which we are creating. So in that image, at location x and y, we want to create a square of size passed as an argument here, and then we will just try to define it and fill it. Similarly, in case of filled square, we will use the same image, and now we will place a square at this location of the size passed as an argument. Okay, similarly for mesh, triangle, circle, and so on. So once we have called all these functions, and we have used the standard image and mask to create multiple images, our data set is ready. Okay. Now, once the data set is ready, the next step is to create a data loader for our model. Okay. So here we have first created the images and the target mask using this generate random data. Then using these input images, so this is how it will look, right? The shape of the image is 192,192,3, and the shape of the target mask is 6,192,192. Can anyone explain why we need why there is 6 here? Any idea? Like why the target mask has to have 6 channels here? So the reason is that there are 6 types of objects: plus, filled circle, filled square, open circle, a triangle, and this is a mesh, sorry, mesh and a square, right? So this target mask is created one per class. So for example, let's say we index plus by 0. Then our 0th target mask will just be a white image with pixels which are belonging to this square is 1, and rest of it will be 0. Similarly, or the otherwise, right? So it's just that you have to make the distinction. Similarly, for the filled circle, all the pixels will be 0 other than the pixels which are belonging to the circle. And therefore, we will create such target mask 1 per class, and this is the reason why we have 6 here. Okay, so input images shape is a simple RGB image, but the target mask shape is the same shape size as the size of the image, but 6 here because 1 per class. Okay, and now once we have this data set ready, we want to create the data loader for it. So the data loader function, what will it do is it will use this dataset function. And this dataset is making sure that whenever the data loader needs an item, it just returns one of the image and its corresponding mask. And if we need to perform any transformation on the image, then that transformation should be performed and returned. Now, here, since we are using a unit, right, we are applying the same transformation as we apply for ImageNet dataset. Okay, because we will be working with a pre-trained unit. It's a high-dimensional network, and training it needs a lot of data. This is just a demo, so we are using a pre-trained unit. For pre-trained unit to work, we need our data to be scaled to the same range as we scale the ImageNet data. So we will apply the same normalization here. Okay. Once we have generated the train set and the validation sets, we are having 2000 samples for the training data and 200 samples for our validation data. Once we have generated this, we will create the corresponding data loaders. Now, just for a check purpose, we can look at the outputs of these data loaders and see how it is working. So, applying a reverse transformation. Okay. Would anyone like to answer why we need a reverse transforms here? Any answer on this? Why we are doing reverse transformation to visualize the images here when we are using data loader? The reason is that this data loader is using this data set, right? And any element which we are taking from this data loader next is coming after so that is nothing but what this function is returning. And this function already applies a transformation to it. So the transformation was normalizing this image. So the image has already been normalized when we get it from the data loader. So visualizing purpose, we need to normalize it. We need to, map it back to the original space. And that's why we are doing this reverse transform. So we are kind of unnormalizing the image here, okay? And then we are visualizing that is the data loader working the same or not. So yes, the data loader is working fine. This is how our image should look. Now defining a unit model. So unit is what this slides were talking. Remember this net here? We have this encoded decoder architecture kind of thing. We have this, so basically we have a downsampling stages, we have an upsampling stages, and we want the feature map of similar resolutions at both upsampling and downsampling stages to be somewhat have skip connections. So this is our architecture of unit. So this unit is being coded here. Sorry. So this unit is being coded here. And it's a big network, so all these layers and convolution and the upsampling is being done. And once you start doing forwarding, you will get an output of the same size as the input, right? So this is the output. So whatever the input you are giving here, you will getting an output, and the output is nothing but a segmentation map, right? So it has the same size as the size of your input image. So similar will happen here. So let's create, we have already defined the architecture of the unit, instantiating the unit model. And this is how this unit is looking. So once unit has been instantiated, okay, this is all the summary purpose. You can look at it. I'll share the notebook. So once this, we have now what all recipe ingredients are needed. So we have the network. The data set is there. The next thing is loss function. So what should be the loss function here? For training purpose, we are using dice loss. What dice loss does is, it tries to make sure that the image pixels it is predicting should be similar to the ground truth mask. Okay. What I mean here is, suppose this is the mask generated, right? For visualization purpose, you are seeing the mask for both the red image, the green part, and the blue part together. But unit would have generated one for each separately. So suppose, let's talk about the zero channel, and the zero channel is only responsible for generating the pixels which are in red. then it will be generating giving the value 1 for the pixels, or a high value for the pixels which it thinks that belongs to this specific class. And similarly is for this input image, right? Mask will be there. So DICE wants to make sure that whatever the pixels are getting predicted should be very close to the pixels which were there in the ground truth mask. And how we will ensure this? So we are taking this prediction into target. Okay, which means that in a numerator, our predicted pixel is getting a preference only if there is a target value. So basically, I predict. So this you can see as IOU, right? So the pixels predicted in the mask should be very similar to a ground. So this is something like IOU, right? Now, when you talk about this intersection over union, so what is there? You have this intersection divided by the union, and this is somewhat your union doing here. So union is doing here in the senses you get the number of pixels you're predicting in your predicted mask and the number of pixels you're predicting in your target mask. Okay, and you also have this the number of pixels which are present in both their intersection, and that is your loss. So when you're trying to minimize the loss, what happens is you are trying to maximize this function, and for maximizing this will happen when this intersection goes high. Okay, because if your ground truth and your predicted is same, then what will be the value here? It will be exactly 1, and this loss will go 0. So the aim of the stats loss function is that your predicted mask should be very close to the ground truth mask. Ideally, it should be exactly same as the ground truth mask for this loss function to take a value of 0. Now, we have defined the loss function, the data is ready, and our network is ready. So the next step is training this network, and training starts here. So we have this epochs, we start the phase, we take the inputs, we take the labels, the optimizer is there. Then once we have this output, we do the loss run backward, we optimize it, we step it, and then we keep on training it for those variables, right? And once the model has been trained, so we need this optimizer, right? So here we are using the Atom optimizer and the scheduler. And once the model has been trained, we can now use it for some unseen images and see how it is doing. So this is how it does for unseen images. This is an image which the model has not seen during training phase. This is the ground truth mask, and this is what the network has predicted. This has been generated by superimposing individual mask predicted by the network, one per class. So this is a ground truth image, ground truth mask, and predicted mask. You can see that though this looks very close here, they are slightly where it is filled, right? It is saying that it has a rounded square, rounded corners, however it has a sharp corners here. Similarly, you can look in this image, right? This edge is a bit shaky, however the edge in the ground truth was a straight line, but even then it is doing a decent well job. So this is this tutorial summarizes training a unit network for segmentation purpose on a dummy data set, where our dummy data set comprises of these black images with some objects introduced randomly in the image, and the objects are nothing but different shapes. Any questions so far on unit segmentation, object detection? Yes, you do need. So when you talk about these object detection methods, right, you have the images, and you know that. Let's go back to the slides. I see. So this is what you are being available. So what is available to the network is this image, 2 bounding boxes. Okay, assuming this is our ground truth as well. So it will be like two bounding boxes. One bounding box for the dog, so its coordinates, and whether it is to which class it belongs. The second bounding box will be this yellow box and the class object, and the third will be this. So as an input, this network got this image, three bounding boxes, and their respective classes. That's all. What it did is that as a processing step, it started predicting bounding boxes per grid cell. So that is the computation it is doing. Now the next question arises: how do we know which of these bounding boxes are the true bounding boxes, right? So when you're talking about this blue box here, uh, you can see that so many grid cells are being covered by this bounding box, right? Now, which grid cell should take the responsibility of this bounding box? The one in which the center of this bounding box will lie should be responsible for predicting this box. Okay. Similarly, the grid cell in which the center of this yellow bounding box lies is responsible for predicting this yellow bounding box. The grid cell in which the center of this pink bounding box lies is responsible for predicting the pink one. So when we are having this class probability map, only the 3 pixels, or not the pixels I should say, the word cell is the correct one. So only 3 cells are responsible for predicting these ground truth boxes, and they should have the class probability map. So these 3 classes should make sure that they're predicting that the class probability for the right object class should be high, and the rest of them should be finalized. Okay. Now when it come about the this bounding boxes, right? So corresponding to these center pixels, right? The pixel where the center lies, that cell is should make sure that it gives the whatever the coordinate is written for the bounding boxes should be very close to the ground truth box, and that happens using the loss function. So if you look at the slides of this, sir, you'll see that there are a couple of loss functions. One is the localization loss, which makes sure that the coordinates predicted of the bounding boxes should be close to the ground truth bounding boxes coordinate, and the second is the class score, that is the score assigned to the object present in the bounding box should be maximum for the truth class. Okay, is this clear now? Okay. Any other questions with unit segmentation and object detection in general? If not, then because less time is left, so I had to cover 2 things in mind. One is this implementation of the contrastive learning, and the second is the assignment 6 discussion. So what would you prefer I should go over? Any assignment discussion? Okay, perfect. So let me open it. Okay, so is there any specific question you want to ask, or should I just start with some random questions and that's how we cover the assignment here? Which question? Okay, the implementation based questions. Okay, so let's go over them one by one. Sorry, can you repeat? Okay, no problem. Let's look at it. So the first question is that you're given a pre-trained EGG model, and the mean of the maximum pixel value across each channel of the saliency map generated using the simple gradient method. And that's what you need, right? So let's go at the implementation first and let's see. Right now, how many people are there in the call? Okay, not much. So this is the question 1. Which of the following values are true? Okay, what is simple gradient method first of all? Would you like to explain that? Hello? Are you there? Yeah, Jyoti. So, what is the simple gradient method is? So let's go back then to the slides because I need the slides here to explain what the simple gradient method is. And let me also open the solutions for you so that I can show you how it works. So this is what happens. So when you talk about the simple gradient method, suppose this is a neural network, right? You give an image as an input. You get the output vector. And that output vector is basically when you apply the software, it's nothing but the probability of the distribution over the possible classes, right? Is that clear? So suppose here is this case. You give a 0 image to the network and you want to do a small update. So what you do is basically you compute the gradient of the function, the loss function here, but with respect to the image itself. Now the question is, what will be the loss function? So the loss function here will depend on the image class you are interested in. So if you want to visualize why this image, or if you want to visualize that how the image of a cat looks to you, then we will set the score vector to be 1 only for the class cat and the rest of them to be 0, and then you backprop to the image. Okay, and then when you will keep on doing this, you will see that for a network what this class cat would look like, right? So So when you're doing all these methods, we are using this simple method called simple gradient method. What is that? Called simple gradient method. So what it expects is that when you give an image as an input to the network, so here what it means, you take an image, you pre-process it, and you give it to the model. But now we will be computing the gradient with respect to the image. So that's why we have said x dot requires grad. Okay, and now when you will do the backward prop here, the gradient of the loss function, and the loss function is nothing but the logits. And here we are looking to the class which is predicted with the maximum probability. Okay, so that's what logits max means. So we are differentiating that with respect to the image itself, and that is being stored in this x dot grad. Okay, so x dot grad contains the gradient of the maximum logit value with respect to the image x, and then taking the absolute value, and the squeeze is just to reduce the dimensionality to 1 because there is only one image, and then you just take the mean and print it. So that will be the value. So it's basically the derivative of the logit with respect to the image and the logit of the class you are interested in. So here they are interested in the class which is being predicted by the model because that's what we are trying to visualize. Is this clear? So this is question 1. Going to the question number 2. So where's the question 2 here? Is this occlusion sensitivity. So giving a pre-trained HT16 model and a test image. Load the image, max predicted label with the help of class probabilities. Conduct the occlusion sensitive experiments with the given mask. Find the position of mask which causes the highest drop in prediction probability. Add the x and y coordinates of the top, left, and bottom right corners of that position and calculate the mean of it. Okay, so what it means? This is just basically the aim of this question is that you are supposed to find the mask by which the probability will drop maximum for the predicted class. Okay. So first of all, answer me. Can you try answering the second question here? Second step. How do we predict the label? Sorry. How do we predict the label with the help of class probabilities? So it is nothing but the one with the maximum probability. Okay. So if their class probabilities are like 0.1, 0.4, and 0.5, then the class which has got the probability as 0.5 will be the correct class. Okay, so this is how you know the predicted class. Now, once you know the label of the predicted class, the aim is to find the region in that image which is resulting in the maximum drop of the in the confidence. So for that, this is how it will look. So this is pre-processing has been done. You have got the outputs. You get the softmax, you get the max, right? And this max will give you the class index of the predicted class, which is 277 in this case. Now the next step is finding the occlusion. Okay, so here you create a mask, right? And that mask is basically you start of a specific size. Okay, so here's what we are doing. And you have an occlusion size. So this occlusion size is basically what will be passed. Okay. And now, once you have this heat map, you start occluding this image and with a map with a size of like say 80,25. Okay. And then you take just the mean coordinate of whatever the heat map you have find, whatever that polymorphs you find, you just find the mean of these values and report. Okay. So if you visualize the heat map, it looks like this, which means that this is the one which is resulting in the maximum drop of the probability. Okay. So if you look here, This is where the animal is present, and that's what we have expected, that these areas should have maximum impact on the probability. Okay, is this clear? And moving on to the third question, which is this occlusion sensitivity, change in prediction with occlusion. So now what is happening is that as you are occluding this image, right? So what occlusion means is that it is an image and you put a black box here. So you select the location and you blacken it. Now once you blacken it, so if it was not blackened, if this was the original image, the class index was 277. But once you blackened it on this area, maybe the class probability of the predicted class changes to 168. So that is this question is asking. So what this question is saying, with the coordinates of the most sensitive positions of the mass obtained in your question, that is once you have find this H-min, W-min, H-min, and W-min, and the question here is that what was the new predicted max label? So how did okay? So what it means that suppose this is the form, this is the square formula. Okay, so if there was no square, the class predicted was 277. If there is a square, what is the index of the class predicted? Okay, so you will again do the max here, and the answer is 3. Okay. So for this, what we will do, we will take the image. We will impose a rectangle using CV2. So CV2 is nothing but open CV. So CV2 dot rectangle will place a rectangle on this image at this location. Okay, and this location we got using this occlusion function. Once we have placed this rectangle on the image, we give this new image as an input to the network and look at the max of the softmax. And the answer is 362, which has changed from what we had previously. Okay. This is clear. So, any other questions in assignments? We can look at it. Were you able to do these questions? Like these simple questions were there? Did you try? Any doubts with these questions? Which one? Applying? Yes, yes. Okay, guided background question you are asking. This one you are asking? This one? 90? Okay. Okay, so here's the thing. Suppose there is an any convolutional layer, and this is the output of the convolutional layer. Okay. And if you apply the ReLU, yes. Yes, perfect. And yes. And there is one more step, that all the negative gradients have to be suppressed as well. So what will happen is that this -5 will become 0 because of -20 in the output, because after that this will become 0. So first of all, let's see, after applying YOLO, what will become 0? This will become 0, this, this, and this will become 0. Okay. Now, next step will be the gradients which are negative will also become 0. So this will become 0, this becomes 0, and this becomes 0. So what is your resultant matrix is? Real ones. Yes. Okay. Any questions? So now you can just fill in that matrix. Okay.